today I'd just like to give a brief solution hint about what we did on Tuesday. So this is the economic problem we would like to solve. We know that there's an income stream which looks like this, and it's already for certain. Today we are in period 1, and the question is what would be the optimal consumption plan for a person with this upcoming income stream. This would be very easy and just standard if we had no liquidity constraint, because in that case we would simply sum up all the incomes we are going to receive in the future plus our initial wealth, and that would be the sum of all consumption values. And since there's a little discount factor, we would get a consumption line which would be slightly downward sloping, such that the total sum of consumption values would equal total income plus initial wealth. But here in this exercise, we have a liquidity constraint. So it doesn't really help to know that we have very high incomes in the future, even though it's already certain. We are, for some reason, neglected the possibility to go into debt. And therefore, we have to adjust our optimal consumption plan. That's the problem. So it's getting non-trivial just because of the liquidity constraint we have here. Okay, a few solution hints. Most of you have already solved the first part of the exercise where you had to derive had to compute the value function. So in this case, let me just briefly reformulate the problem in the standard language that we have introduced in the course. We have a control variable, we have a state variable. The control variable in this case is, of course, consumption, because we can choose consumption in each period. We have a state variable, wealth, which is given in the initial period and which evolves just according to the law of motion. And we have the income path. And then the question is, what is income? And I think it's best just to think of income as part of the law of motion, because in the law of motion we have this t here, so the law of motion might depend on time, and here the time dependence just means that we add in each period the income of that period, which is known in advance. Okay, so the law of motion is very simple. We don't have any interest rate, or the interest rate is just 0. So tomorrow's wealth is today's wealth plus income of today minus current consumption. That's the law of motion. Okay. We need to know the value functions to solve this problem. And we've already seen that the best way, if you have a finite time horizon, is to go backward. And that means we start in the last period. In the last period, it's trivial to derive the value function, because the value function is always the maximum you can get out of the sum of current utility plus the value of the rest. But there's no rest in the last period. So it's just the maximum utility you can derive, which means you just consume everything. In the final period, you have a final wealth WT, which is as yet unknown. And therefore, the value function is just a function of this final wealth plus the final income. So this had to be programmed. And then for all earlier periods, we just go backward period by period. And each time we solve a maximization problem. And in the notation of this setting, it's pretty easy. We have current utility. There's the discount factor missing plus beta times tomorrow's value function, evaluated at tomorrow's wealth, which in turn depends on current consumption. Right? So that's just a reformulation of our problem. Then the important question to solve in this exercise was, how can we represent the value functions in R? And there are, of course, a large number of possible solutions. The one that we suggested here is to stack the value functions, the 30 value functions on top of each other into a vector of functions. So in that case, we have a value function for the first period up to the last period, and they are represented as elements of a very, well, general kind of list. So we regard this as a vector of functions. So the first element of that vector can be accessed by using the double bracket notation, evaluated at position 1 up to the last position. Or we use double T, I think, here. Okay, so that would be, I think, a very very neat way to represent the entire family of value functions in one object. So this object would just be called V. And then we can, once we have these value functions, which as now, as yet we don't, but once we have them, we can evaluate the function at position t, so the value function of period t for n by simply typing this. So this means use the object v, which is the vector of functions. Just use the tth element, which is the tth or the value function of period t, or double t. And then this is a function. So we can actually use it just like any other internal function in R, and just use the round bracket notation to put an argument to that function, to input an argument into that function. So in that case, we just use W and evaluate the value function for period t at any point W. So that's the R equivalent to this notation here.
May I ask a question?
Yes, sure.
That we also, I think, in one or two groups I stumbled upon on Tuesday. Suppose, I mean, you would have typed instead of just picking one of those list objects, you would just have written V round bracket W round bracket. Would that produce an error, or would R know, okay, I go through all the elements and tell you basically a list of numbers once if the V objects are suitably usable?
So the question is, what would happen if I drop the double bracket notation and just type V of W?
Yes.
It doesn't work. And the reason is that, well, V is actually not known as a vector of functions. We just interpret it as a vector of functions. Internally, it's just a list. And a list could be anything. So,
okay. So you cannot address the list as, so R doesn't know that the list of functions could be used as a list of functions. Basically, it just knows, okay, it's a list. So yes. I cannot. Okay. Thank you.
So a priori, it's not clear that the tth element of that list actually is a function. Could be anything. And if we actually extract the tth element, then it's clear that it is a function. But we have to do that. So without using the double bracket notation, it's not clear that this list V is a list of functions. So it would be nice. Maybe I guess in some programming languages, it's possible to define such a list of functions, but in R, I think it's not. At least for this exercise, we haven't done so. Okay, so now we have to fill this vector of functions with functions, because when we start, the initial vector is just empty. So we start in the last period, and all of you have done that. So in the last period, it's easy, and we just assign a function of W to this element, and the value of that function, or the return of that function, is the utility evaluated at W, so the functional argument, plus last period's income. And then for all earlier periods, we do not know the functional form of the value function, and therefore we have to approximate it. And we do so by linear interpolation. There are other methods, of course, but here we taught you to use linear approximation. So we need a grid, and in the exercise there was grid was defined over the interval from 0 to 200 with fine little steps. So we can use the proxfun command, which actually returns a function. And this function is then written at the tth position of the object. And we need a second argument. We need to know the functional values at the grid points. So these are called just values here. Values is a vector in this case, but when we start, we do not know these values. So we have to compute these values. How do we do that? Well, we have to solve the optimization problem. Yeah, just go back. To know the values of the value function for a grid point W, for some grid point W, we have to solve the right-hand side, which means we have to solve this optimization problem. And we have to maximize what's inside the square brackets. Yeah. And let's call that the maximum. This is what's inside the square brackets. And of course, this depends on current consumption. That's our control variable over which we would like to maximize. And it also depends on current wealth, which is the argument of the function. So the current grid point we are working on, plus current income, which is known, minus the consumption, which is again the control variable. So that appears twice. And tomorrow's value function. So the maximum depends on 4 different things, plus the discount rate, current consumption, or the consumption, the control variable, current wealth, current income, and tomorrow's value function. So this is actually, that's a bit misleading maybe. This is not the object V. This is just here, it's the same notation, but here, this is just an argument of the function. So this could be a function, this is a function that's given to the maximum as an argument. And then what we return is, of course, just this here. And again, the discount factor is missing. So it's the utility of the current utility plus the discounted value of next period. And next period's value function is V. That's the one which is here given as an argument of the function. Okay, so the arguments are consumption, over which we maximized, then wealth, income, and next period's value function. If there are any questions, just
yeah, I have.
Yeah,
Just
sure.
want to the V thing. So basically, what we are doing here is the V is the in this list notation, the V square bracket capital T square bracket.
Yeah.
Okay, and because there I think there was the situation that puzzled me. Because I thought, well, is it how does R know that it's supposed to pick the right element out of the V, and so the solution is it doesn't. It's just another definition.
Exactly. Yeah. So maybe it would have been better to use a different symbol here to make really clear that this is not the stack of functions, but this is just an argument of the maximum. Okay. So now we have to optimize over consumption, and we have to do that for each grid point, because to know the value function, we have to know, at least at the grid points, the value of the value function. Yeah? So we have to evaluate, and we have to solve the optimization problem for each grid point over the wealth grid. So we run a loop over all grid points, and I think all of you have done so. And for the grid point, for the ith grid point, this is the command for the optimization. So we want to maximize the maximum. That's the function we've just defined. And this is the interval over which we would like to maximize. We know that consumption must not be negative, because then utility would be minus infinity. Actually, at 0, it's minus infinity, but let's skip that problem here. And the maximal amount of consumption is to just consume everything that's available in that period. And this would be, well, the wealth, if we start at that grid point, plus income in that period. And then the other arguments of the maximum are the current wealth, which in this case is just the value at the grid, current income. And here, this answers Jörg's question. So the argument V in this case is just an element of the object V, which we defined before. So that's one element of this stack of functions. And then, of course, we have to maximize rather than minimize. And what we get is an object. Here it's called just object. And it has two or even more ingredients. One of them is objective. That's the maximal value. And this is what we're interested in. So we just store that into some kind of vector. All groups, I think, have used different names for that. Here it's called just values. And we do that in a loop over all grid points. And then, after we've done so, we have all the grid points and we have all the values. So we know the value function for period t at all the grid points, and we just use linear interpolation between the grid points. Yeah, that's already it. Just very briefly, I'd like to show you the R code. It's ordered in a strange way. Can you see the R code now? Can you see what I just marked?
Yes.
Good. Okay, so this is just what all of you, I think, have already done. So we have the backward recursion from t-1 down to 1. We have the maximum. Then we have the grid over the loop over the wealth grid. And then finally, the approx.fun command. The additional argument rule equal to 2 is, I think, not really necessary. It just makes sure that if you should evaluate, or if you just happen to evaluate the value function outside the grid, then you just use the outermost values. Let's run that. Takes a little while. So you can see that even this non-stochastic problem takes a little while. And if you want to evaluate the value function for the initial period, for an initial wealth of 3, what you get is minus 3.8 roughly. So don't be surprised, the value can be negative here. And now the next question is, and I think not all groups did that. So just let me give you, let me just briefly sketch how one could do that. What would now be the actual optimal consumption path? Because we haven't really solved for the optimal consumption path, at least not yet. So if we want the optimal consumption path, we have to solve this optimization problem, which means that we have to optimize over consumption, maximize over consumption, the sum of current utility plus discounted value function of next period. And we can do so now for every period, because now we have all the value functions. Yeah, so now we are in a position to solve this problem for any period. And we also know the wealth. In the initial period, it's 3. Then we can find the optimal consumption for the initial period, which means that together with the known income, we get the wealth for the next period, and so on. Okay, so what we need is a wealth path, that's this one here. Then consumption path, this one here. Then we start with initial wealth of 3. So if we use the abstract notation, we would use period 0 for the current period, but in R it's better to use period 1 because you can't use 0 as an index. And now we have a loop over the periods, but running forward. We start in the first period up to the last but one period. In the last period, we just use the rest then. And for each period, we have to solve this optimization problem again. So again, we define the maximum and we solve the optimization problem. So this is exactly the same as before, but now we don't extract the objective value of the object, but we extract the maximum argument or the maximum element of this object. Yeah, and the maximum means that's the value where the objective function is maximized. So in short, this is the consumption in period t. We write that into the consumption vector of period t. Then we use the law of motion to get the wealth in the next period, and we run that over all periods. Let's run that. So that's really fast. And in the final period, we just use consume what's left over. And how does the consumption path look like? Looks like this. Yeah. So this is the outcome of what you have done on Tuesday. Not all of you have seen this consumption path yet, and it's complicated. Yeah. So it's roughly constant, slightly downward sloping at the beginning. Then there's a jump, again slightly downward, jump again, and a couple of jumps again. How come it looks like this? Well, that's of course a consequence of the liquidity constraint. This would be the time path of incomes. So we start with low incomes, and towards the end we have higher incomes. But we can't use these higher incomes because we can't go into debt. And therefore we have to start with relatively low values of consumption. Okay, so there's a bit of consumption smoothing going on here, because we can, with our initial wealth of 3, we can smooth these fluctuations of the income stream, and then we can jump, and from time to time we can jump. Okay. Can also see that the value of total consumption is equal to total income plus initial wealth. So this 3 is initial wealth, and that's true. Okay. So what would happen if initial wealth was larger, say 50? Well, in that case, the liquidity constraint is less binding, so the jumps won't happen that fast. And you can see that the consumption path goes up. But then at some point, the liquidity constraint is binding again, and therefore we still have these jumps towards the middle periods or towards the end. Okay. If we increase wealth even further, say to 100, it goes further up. If we increase it even further to 200, looks like this, but still there's a jump at the end. And that's because at the end, we have these very high incomes, and we can't make use of them earlier because we can't go into debt. What would happen if we increase our wealth beyond 200, say to 250? This is the sum of total incomes. Then something strange happens. You can see here that initial consumption would be very, very high, and then it would drop going along this path and then going up again. This is absolutely not plausible, and actually it's wrong. And why is that? Any ideas? Stop the sharing. Any ideas? Why doesn't that work? Well, the answer is look at the approximation of the value functions. You did that by linear interpolation of a grid of wealth values, and the grid was going from 0 to 200. Yeah, but now we started at 250, which is outside the grid, so we actually don't know the value function, and therefore we cannot solve the problem. Yeah, or if we just ignore the problem that our approximation is blatantly wrong, then of course we just get nonsense. And this is what we get in that case. All right. So I think we upload the solution file for the program, but at least the first part has been solved for all of you. All right. Any further questions?
Yes, actually one. In the slides you've just shown, slide 6, for the last periods, you didn't include the beta. So could you just tell me once again why that was?
Because I forgot to do so.
Okay.
that was a mistake.
Okay, good. Thank you.
Good question. Yeah, I think I should correct that. Okay, so if there are no further questions, I hand over to Jörg, and we start with the infinite horizon case, because that's actually, it's surprisingly that's easier than the finite horizon case, I think, at least the numerical treatment, not the theoretical one, but well, you will see that.
Okay, thank you so much. First of all, before we come to that, let me thank you for the very illustrative presentation. And one thing I would like to add, just for, I mean, we as you might already have perceived, that we have a that we have different comparative advantages, so to say. So I'm not the guy who's doing the numerical things, but I have to admit that if you have the capabilities of also being able to solve those problems numerically, you really increase or you super much leverage up the questions that you could answer, because the question that we just had, this liquidity constraint, is, I think, very relevant if you think about real world applications. So there are definitely liquidity constraints. You cannot go, even you're accumulating human capital, but you cannot borrow against that, because you do not have any collateral. And I mean, you could do that by pen and paper, right? But you would have to consider 30 inequality constraints. So for every period, you have to make sure that you do not run into debt. And if you are familiar a little bit with Kuhn-Tucker inequality constraints, then you might know that you basically have to test in every period and for all periods, and the complete set which of the constraints is binding. So I mean, it is conceptually doable, but it's not feasible. I mean, you won't have that much time. And I mean, going back to the original problem, I mean, we just now spend, I don't know, 2 hours or so, and suppose without any guidance, we would have spent a day or so. That is a killing compared to the pen and paper thing, because that would take you years. If it would even be possible, and it wouldn't not only take you years, but you could just, you know, in the numerical applications, you could easily change things. This is not doable in the theoretical case. So I think this is a great example, showing you or making really the point why it's definitely valuable to have say both weapons at your hands, because just focusing on the theoretical issues is helpful, because you understand a lot of things, but you have to very much focus on a very specific set of questions. And once you want to answer different questions, it is very difficult, right? And this just opens your so to say, your intellectual space of doing different things. So I think this is an excellent example of this, a problem that is seemingly super easy doable, which with a simple real world extension wouldn't be feasible to do that. So thanks again. I think that was very very helpful. Okay, so having said that, can you see my screen? go to presentation mode.
Yeah.
Okay. So having said that, we will now extend a little bit our approach. And what we are trying to do, what we are going to do is we just make again a relatively simple extension at first glance. So what we want to do is we want to get rid of the potential restriction that the planning horizon is fixed somewhat, but that we have an infinite horizon an infinite planning horizon, so that time basically goes to infinity. So there's no end, there's no last period. Okay, so why do we do that? Well, some problems that we might encounter are in a way better approximated by an infinite horizon. That could be consumption choices when you buy the point that what you have in mind are so to say your family dynasties, okay, that you're planning for your kids and your grandkids and so on, and that you want to leave a bequest and so on, then it seems to be fair to approximate this by a planning problem where there's no end. But also in other applications, it might be valuable to have an infinite planning horizon. On the one hand, this is somewhat good. Okay, this has the advantage that we do not have to think about what happens in the last period or what happens in the last but next period. So all the things that we considered, where we talked about how to value the rest that you leave after the planning horizon is finished, we get rid of that. That's good. But at the same time, this is obviously the big disadvantage, because thinking in solution strategies, we are really not able to have an anchor anymore, right? In the solution strategy, be it the theoretical approach or the numeric approach, we needed to have this last period such that we could that we could specify the value function for this last period, and using this anchor and go recursively backwards through time to generate basically the set or the vector of the different value functions for the different times. This is not possible anymore, obviously, because there's no last period. This is one problem, and the second problem concerns the objective function, because you somehow want to make sure that at the beginning of your planning horizon, so at some point in time where you are thinking about the optimal control path that you want to implement, that somehow this sum of all the contemporaneous utilities that you would receive converges to something. So when you look at at our initial problem, which was here, okay, so if we just get rid of the capital T and call this infinity, then obviously it could be a problem that the expression in the square bracket, so the sum of all the contemporaneous utilities is infinity, okay, and it would be infinity for every control path, okay. So in this situation, it wouldn't make too much sense to think about optimal control sequences, because you knew, yeah, well, I have an infinite amount of time, so it doesn't really matter anymore. I think last time we briefly touched, at least Margrethe and I briefly touched the movie Groundhog Day. Maybe it's relatively old, so I guess most of you may or may not know the movie. There we had the situation that this TV guy is caught in a time loop because he's a bad personality, basically, And what he does every day, he wakes up every day, he lives the same day over and over again, and he knows that so he has no insomnia, so he doesn't forget anything. So what he's doing then in the course of time, he learns languages and play the piano and do a gazillion things. So this is a problem where the value function would not converge, right? So there's no optimal plan. If you live for infinity, there's no optimal plan on what you do, because it doesn't matter. Okay, you can allocate your time on learning the piano, learning languages, I don't know, building bridges, whatever you want to do. There's no point in thinking about optimal control sequences. So what you need is somewhat an adjustment of this of your objective function. I just want to say value function, but this is not really true. So the objective function. So what we have is, if we look at those problems, and this is the second bullet point, and please just focus for the moment on the second bullet point, and we come to the first bullet point in a second. So we want to make sure that we have some limit on the sum of the contemporaneous values. And in economics, and I'm not sure how other scientific disciplines achieve that, but in economics, usually discounting does the trick. Okay, so what we assume here is that this limit of the utility sum is achieved by weighing the further distant utilities by a smaller and smaller amount. So it could be the case that you have this super large utility sum in the very far future, which adds to your sum. But since the weight that you put on that is so super small, you have a situation, or you might have a situation where there's a limit on this sum, which is good, because then again we are back in business, right? Because if there is some limit on this objective, well, then it should also be the case, or it should at least matter which control sequence you choose, because obviously the limit is basically a number. Okay, so by adjusting your behavior, you could pick the largest number that is possible given all the constraints that you have. So this is one qualification that we need. We somewhat have to make sure that this is the case. As I said, in the problems that we encounter, this is usually the case. So I'm just telling you that that you are aware that this could be a problem. Okay, but that this is not necessarily always the case. Another problem or another assumption that we make, and this is I think crucial for the arguments that we will talk about in a second, is that we look at so-called autonomous problems, which means that that time just by itself has no direct effect, neither on the contemporaneous objective, so neither on the contemporaneous utility, nor on the law of motion. Okay, and when preparing this, or what I wanted to talk about today, I thought about whether this is very restrictive, but I think it's not. Okay, and I tell you an example why. Maybe it's a good example, maybe not. So think about a situation where the utility function, so the parameters of the utility function, or the utility function somewhat, the form of the function evolves over time. Okay, so basically your preferences change over time. Then it could potentially be the case that time enters directly into your value function. Well, then this could be a problem. But I think that in many cases you could reformulate this problem, okay, by formalizing this direct time effect as an effect on as interpreting this as a state, okay, and using this separately. So again, I think it is important that you see this point. So this autonomy, is it called autonomy? So this autonomous problem just implies that the general nature of the problem does not change through time. I think this is the intuitive reason, but I think that this is not too restrictive, I would say. So this is it's not too bad an assumption. Okay, so the first thing that I want to show you now is when we consider this infinite horizon problem, that and it is autonomous and it converges and everything is nice, that basically we have a situation. So this is the first intuition, that we have a situation that basically the problem that you want to solve, so the situation that the decision maker is in, is basically identical in every period. Okay, the only exception from this identity, so to say, is that the state changes. So the thing is, if you move your system, so your objective function, so what you do through time, then it does not change really. The only thing that changes is the state that you are in, and obviously this gives rise to changes in your control path. But if you took this into account, then this should not affect any of your choices. So basically, I think in a more, say, economic reasoning, one would say that the problem is time consistent. Okay, so it does not change through time. So given that you are a decision maker and you could travel through time, okay, and you follow the optimal path, and you think, okay, would I change things given that the state that I'm in is the same as before? Then this should not change anymore. Obviously, if the state changes, well, then things are different, right? So again, I guess you are too young to think about those things, but sometimes you may consider what would you have changed things in your life, decisions in your life, if you could travel back through time? Well, then obviously this is true, but this is not necessarily true because your preference or because the intertemporal problem changed, but because the state of things that you know changed. So the relevant question in this context would be, would you change things if you travel back through time, given that you have the same knowledge as before? Okay, and this is the only fair comparison, right? And what we would say is, or what we assume is, that you would come to the conclusion, no, I wouldn't change a thing. Okay, so this is the basic idea, and in technical terms, this is called the principle of optimality, and this is the one of the more important insights, I would say, of the dynamic programming problem with infinite horizons, because I think this is the thing that really helps you, and I think also that this is an assumption that just makes it possible to really find a solution to those problems. Okay, so this is the general idea, and what the plan is for today is, I just want to talk briefly about the intuition behind this principle of optimality, and I want to talk a little bit about the challenges that you might face then in finding the optimal path, and how a solution in finding the optimal path then could look like, and why then this principle of optimality that we are just going to talk about is very helpful. Okay. And again, if you have any question or suggestions, just unmute and tell me what you think, or what you want to know, or whatever thing that you might want to consider.
I think I have a question.
Sure.
Can I think about these beta factor as a kind of impatient rate? You know that, for example, if beta is very small, I'm very impatient, and I only value, you know, consumption, for example, which is pretty close to my period now.
Yeah.
Okay, cool.
Yeah, this is just a time discounting. This is just time discounting.
Okay.
But you need this discounting factor somehow to make the objective converge, right? Again, if this was not the case, so if you would push for a situation that you would say, okay, I value the future consumption of my future offspring the same way as I consider my consumption. Well, then there's no point in planning anything. Then then there's no optimal consumption path, because there's no. Why would you think about optimal consumption path? Because they just you can pick anything, and everything will optimal. And every of your children and of your offspring can also pick anything, because the sum always converges to, or always goes to infinity. So it's pointless to think about any optimization. Only the inclusion of the discounting makes the problem sensible, I think.
Okay, thank you.
All right.
Sorry if I could, just to be sure I get this right. So this assumption allows us to not just pick an arbitrary date in the future and then say, okay, this is our last period, just like we did before, and now we go back. So basically, this is the excuse to say, okay, we don't do that. We start from 0 and then we'll see how it goes.
I see. Oh, you could. I mean, this is just an example that you pick 0 here. You could pick any date, right?
No, I mean not the 0, but just that we discard the principle of picking a date in the future and then going back. This is the
exactly, because
okay, good.
There's no. I mean, you could do that, but then you would have the problem. Okay, if I pick any date in the future, there will be a date plus 1. So you cannot use this as your benchmark, so to say, because you would say, okay, given I die in this period, well, then this is a good idea, because I just can go backwards. But if you think, okay, there's more to come, well, then there's then you cannot just pick one point and move backwards, and there's always more to come, right? Because it's infinite long. So well, it's not necessarily uncountable, but it's just infinity. You always find a next period. There's always a next period.
Okay, thank you.
Okay, so again, the main insight here is basically that if you shift your problem. So if you say your planning horizon, or your start of the planning horizon is 0, it could be any date, right? We just normalize the start to be 0, okay? Then you could obviously shift your this problem through time, okay? And then you could ask yourself, okay, how would that differ when I shift that through time? Will it be will the value that I would achieve, that I would attach to this situation be different when I'm at the new planning horizon? Would the value that I attach to this situation then different than the value that I attach to that today? Except for a change in the state variable. This was super complicated, but you see in a minute what I really mean. So you basically consider 2 situations, okay? So you are in period 0, okay, and you ask yourself, okay, when I'm in period tau, what is then my objective? Okay, how would I think today in period 0 about the situation that I'm in period tau? Okay, and this is obviously just the discounted sum of the rest of your utilities that you would achieve starting in period tau. Okay, and discount this value to today. Okay, so this is basically what you are going to do here. So this is basically the present value of a control sequence starting in tau. Okay, so you are in 0 and you think about what would be your best control path in 5 years, and how do I value that? So how do I think about this situation in 5 years? Well, this is this, right? So this is everything you achieve starting from the 5 years, and you discount every utility stream, every contemporaneous utility up to today, so up to point 0. Okay, and you could do the same basically with a situation saying, okay, suppose that I'm not in 0, but I could travel forward to time into 5 years, into being in 5 years. What would then be the value of this sequence that I've chosen? And this is obviously this thing. Okay, so every utility stream that you would receive from there on is discounted to point in time 0. Okay, so the only difference basically between the two objectives is obviously your discounting. Okay, so this is like saying, okay, I can take this value that I value, I can use this objective that is valued in period 0 values, and I know that the only difference between those two objectives is obviously discounting. Okay, because I look at the same problem, right? I just take this problem and I move myself through time and think what would be the best thing to do given I face this problem. Okay, and in a second step, you define two control sequences. So you define the control sequence that maximizes your utility streams, for example, in 5 years, as seen as from today. Okay, and the other thing is you maximize your utility stream in 5 years, being in a situation in 5 years. Okay, so the only difference between the two situations is that you look at things from today and plan for in 5 years, and the other thing is you are in 5 years and plan for the future. Okay, and I'm not saying here that, and this is, I think, also not at least at this point, not super relevant. I'm not saying that the control paths are the same. Okay, so this holds for general control paths that are maximal. It could be, for example, the case. It turns out that it's not, but it could, at least in this situation, in general, be the case that the optimal control path that you pick in period 0 for what happens in 5 years differs from the control path that you pick once you are in five years. Okay, so these are just the values. But since I have the relation between these objectives, that they just differ due to the discounting. Okay, I could plug this in here, right? And using this, I could write down a relation that I have between the optimal value of the path, say in the future, value from today, compared to the optimal value starting from the future. And the only difference is I have to discount everything that starts in the future to today. And this is due to the fact that that here these objectives are the same. basically. They do not differ. The only thing that matters here is obviously what would be the state here. Okay, so basically those two problems are the same. So whether you are in in 5 years, or whether you arrive finally in 5 years and then start planning. Although again, it could in principle be the case. I think it's not. It could in principle be the case that the plans that you have written down in 0 for in 5 years, and the plan that you wanna pursue once you are in 5 years, might look different. Okay, so one of the value functions is the standard value function. I think there is a typo. It must be v index 0 and a superscript 0. This is the standard value function that starts in T0 and choosing the. No, hold on. Sorry. No, this is the standard the present value value function that you have, and you start just in 0. Okay, so there's basically no difference between the two, right? And you have the situation that you shift this problem through time. So instead of being in 0, you argue, okay, what would be the situation if I'm in 5 years? Okay, and what we argue, or what we claim, and which is proven in the Sidesetter et al. Textbook, and it's not too super complicated. It's relatively easy to prove as far as I remember, but it's a bit tedious. That we claim that those two problems, so the value of being today and the value of being in 5 years, given that the state is the same, is identical. Okay, so what we assume is that the value of the shifted problem, so everything that you do and the value that identical to the problem that you would encounter in period 0. So it doesn't really matter for the value itself if this problem is shifted through time, except for the case that the state obviously might change. Okay, and this is why we need this somewhat maybe at first glance counterintuitive notation, that we need this v superscript tau, because this is not the present value of the value function, but the current value, so to say, the current present value of the value function, because it takes discounting just to the future point in time that you consider. In this case, it would be tau. So in our example, it would be 5. Okay. And what you then do is you use basically this claim and this definition. So this definition, okay, and this claim to show that the value function we've worked with so far, that we've derived so far, is the same. So the functional form, so to say, is the same for any period in time. Okay, and this is what I want to show real quick. So suppose that you are in period 0. Okay, so so you discount everything what happens to period 0. Okay, and we said, well, this is v superscript is v superscript 0, which is the same as v index 0. Okay, is just the maximum of the contemporaneous utility that I would receive, plus the value that I would have in the next period, discounted to today. Okay, because obviously it is the case that this continuation value, so the thing that you would receive in the next period, that you have to discount that you have to value that in current units, right? But if you value that in current units, well, then you could just, because this was the definition that we used, right? You could just write this as beta times the current value function. Okay, so the only difference between those two things is that that this is discounted. Okay, so the only difference here is that you value this in period 0 units, and this is valued in period 1 units. Well, but then you have to discount this to value everything in period 0 units. Well, and the last step that you use is the claim that is proven in the textbook, the shifted problem. So if you shift the problem through time, that this does not change the form of the value function, as long as the state that you are in is identical. So instead of writing v superscript si, you could also write, well, this is v0 v superscript 0 si. So the problem that you are in tomorrow is the same as the problem you were in today, if and only if the states that you experience are the same. Does that make sense? So you basically have two ingredients. First ingredient is that you could just revalue the same value function through time. Okay, this is one thing, and the other thing is that the general problem, so the value that you would attach to an optimal sequence, does not change if the problem moves through time. Okay, and if you do that, well, then we basically come to the conclusion, because this is just a normalization, right? That this is 0. So this is the period that we are in. It could be any period that we are in. Okay, so this basically holds true for any point in time. So what we can do is we can just get rid of this time index, so to say. So there's no time anymore involved in the form of the value function. It's only involved in the indexing of the state and of the control. Okay, and this is obviously due to the assumption that the problem is autonomous, right? So time does not directly enter this problem. Okay, so if you want to consider things that change over time, you have to put them some way or another into the state, right? This is the important insight. So basically, this was the definition, okay? And from the second line to the third line, this was the assumption or the claim that the problem won't change if you go through time and keep the state constant. Okay, and again, in my maybe very ignorant view, I would argue that this is a consequence of time consistent planning. Okay, so any time inconsistency would change your problem. So if you had asymmetries in your discounting somehow, then things tend to go out of hands a little bit. Okay, so what we then can do is basically we can get rid of the time index and have a formulation that says that the value that you experience, so the optimized objective at any state that you are in is just the contemporaneous utility plus the discounted value that you are in tomorrow, having chosen the control optimally. And again, the cool thing with the recursive formulation is that you do not have to consider any sequence. And the additional cool thing in this autonomous infinite horizon problem is that you do not have to consider time, time, so to say, is just summarized here in this expression that tells you how the state of motion. Okay, so you basically do not have to consider really time. Okay, so this is relatively straightforward, and again, we could pick just one control and could write down first order conditions. I'll show you that in a second. And once we knew how this functional form, which is the same every period, this functional form, how you value your future and everything that happens, is the same through time. So it doesn't change as you move through your planning horizon. So if we knew the functional form of the V, then the problem would be very easily solved, right? You could just focus on this expression, so on this right-hand side, and you would just write down one first order condition, and then you're good to go. Very simple. Okay, so the only thing you need to consider is one first order condition plus the law of motion. So that would be super easy. Okay.
Maybe we should already add at this point that this Bellman equation is also, once you understood that, then I think the most important things of this course are already there. And this is also more or less the basis for the reinforcement learning later on. So we have to refine that a little bit because we want to take stochastics into account and randomness, but it's really just a small step to do so once you've understood the deterministic case. So this is it.
And the thing is, it looks very innocent, right? At first glance, you would say, yeah, super intuitive. No, I mean, it doesn't change. You need this the value function, and everything's very easy. But actually, it looks easy because people invested a lot of time to structure this problem in such a way that it looks easy. Okay, and please never underestimate this achievement. Right? I mean, everything looks or is simple once you know it. Okay, walking. The example that I always use is, walking upright is super easy. You do not have to think about that. Look at your half-year-old child, then you see, okay, it's not super easy, obviously, but this is as always the case. So I think we cannot stress this enough, that this is really the key element of more or less everything, more or less that we want to say. Okay, so the elusive quest somewhat is how are we able to find this V? And later on, this V is a little bit more complex when using when implementing stochastic things, and but these are, as Mark said, I would also say refinements, more or less. So you add a little bit here, a little bit there, but the general idea is the same. So we always have to, or this will be basically the rest of the course, thinking about how to get an expression for this V, because again, as was true with the numerical implementation that we had with the finite horizon, this was the same idea, right? Once we had the form of the value function, the rest was fairly simple, right? This is again, if you know it, then also the implementation of finding the optimal consumption path, as just shown, is relatively simple. And one indicator is, for example, how long it took in the first approach to find the value functions for going through the list, which took a fair amount of time on the one hand, and then afterwards finding the optimal consumption path, which was very fast. Okay, so this is the main problem: how to find the value function. But even if we did not know the value function explicitly, we could at least learn a little bit in general how the optimal control path would look like, or what are the things that an optimal control path has to fulfill. And to do that, and this is based, this is just for that you get a complete package. So we can focus on the right hand side of this equation and just write down the first order condition, not knowing obviously the form of the value function. So in terms of finding the solution, this is obviously a totally a dumb idea, because since we do not know the form of the value function, taking this derivative of finding some best element, however you want to do that, is a bit pointless, right? But maybe I walk you through that, and I try to convey that maybe it's a little bit helpful, right? We do the same as a last time order condition of the control situation. So this just again trades off the immediate effect that that an increase in the control has to the rest of the planning horizon effect. And what is the rest of the planning horizon effect? Well, this affects the state that you are in. The change of the state affects your continuation value, so how much you value the rest of the planning horizon. Well, then you have to discount that. Okay, and this gives you the control function as a function of solely the state. Okay, so here would be the tomorrow's state, and you could plug this in here into the value function. So you plug in the maximized control, and then ask yourself, okay, what would be the windfall gain? How much would you value a windfall gain of the state? And you have here again an envelope condition, and then you would get a relation between basically the slopes of the value function, because this is evaluated at the state today and this is evaluated at the state tomorrow. And again, if you knew that, well, then you could directly solve for the consumption path. But obviously, this is a thing you do not know. Okay, but you could plug this in here and using the first order condition, and at least derive a relation that must hold along the optimal control path. So what you cannot do is you cannot directly solve for the control path, but you have an equation that tells you something about the slope of this path. And this is again called the Euler equation that we had before. And this is basically you would have a difference equation that you could solve in principle, at least if you have problems where these derivatives and everything exist. Okay, again, taking into account non-negativity constraint and strange problems, whatever strange means in this situation, is relatively challenging. Okay, so this is the main point, I would say, of today's lecture. This is just to show you what we already did before. It's the same approach. You take the first order condition, you play around a little bit with how the value changes as the state variable changes, and then try to derive some difference or differential equation for the control path. Okay, so This is a thing you could do, but as I said, you need to have this. You need to have differentiabilities. You do not want to have non-negativity constraints or crazy constraints, and the problem should be in the broader sense well defined. Okay, so with all those problems, you could solve for the optimal path without necessarily directly knowing what the value function would look like. Okay, this is possible. Okay, so I told you that it would be super helpful to know the value function, but in some problems it's not necessarily super decisive. Okay, if you think about a very simple, say, Ramsey growth model, you could solve this using a Bellman equation without explicitly writing down the value function. Okay, and I guess if you have macro masters courses, basically this is a thing that you might have come across maybe. Okay, so what we want to do here is, however, we want to, as I said at the beginning, also broaden our perspective a little bit. So maybe we do not want to restrict ourselves to those special problems. Maybe we also want to don't want to attack the problem directly, but maybe it would be helpful to find a way, a more general way, maybe to solve those problems. And the basic approach would be, as before, well, let us find the value function. Okay, the value function is basically the unknown thing in the Bellman equation. And once we know the value function, so the form of this function, it's very easy to find the optimal path and find everything that you need to know. The problem is obviously that the value function is defined as the value function. So the value function is so to say a function of itself. So it's not that easy to find a solution. Okay, and it's also at first glance totally unclear how we could do that. How we could, I mean, you know how to find unknowns in systems of equations. Okay, where the unknown is just a number, or where the unknowns are numbers. Okay, then you could solve that somehow. The unknown here is basically the functional form. So how this object looks like. This is basically the unknown, and the unknown is defined as a function of itself somewhat. So in a very simple one equation problem that would be very easy, right? Say that was a number x, and this is defined as the maximum of u plus x or so. Then it would be super straightforward to solve for the x, right? But here this is not possible. I mean, this is not, you need to come up with something else. So if you want to know how this function looks like, well, then we have to think a little bit harder how to do that. And at the end of the day, it turns out that it's I mean the math behind that, I think it's relatively complex, and I cannot show you everything rigorously. I just give you a very short hint of how we can think about that. But it turns out, surprisingly, that it's a very simple algorithm behind solving for unknown functions, at least in this context. And the great thing is that this relatively simple algorithm is also very suitable to, as always, as with any algorithm, is very suitable to put it in a computer. Okay, and before we come to that, let me just give you let me just start with a very simple idea of how to find this unknown functional form. Okay, and the idea is just that that this solution of this functional form really exists, and this is I think the main point here, that any starting function, so any functional form that you start with, converges to the optimal solution. Okay, so you could, for example, come up with the idea saying, okay, maybe this v is quadratic, so maybe this is just the m of s comma c to the power of 2. Then what you could show is that using this maximum operator, okay, you would generate a new value function, and if the new value function is the initial value function, well, then you have the solution. And what you know is this solution definitely exists, and irrespectively where you start, you could use this algorithm over and over again until you eventually find the functional form. Yeah, that will become more clearer later on, and we will talk a lot about that, how that works. But for the moment, do you have any questions concerning this general idea? Everything's clear? Okay, then let me briefly walk you through the. We only have 10 minutes left, so I will be very. I will be just very brief about those things, and I'm not sure whether we cover everything in the 10 minutes or so. We will see. What we are going to do is we prove this thing in basically in 2 steps. We are just I'm just going to show you that that any function converges to a fixed point of the functions, given that you apply a very specific operator. And I will tell you, and will not really show you, that this specific functional operator, so the operator that you use on the functions, that this operator is the same as the maximum operator in the Bellman equation, which is basically the idea why we could apply this insight on finding the form of the value function. Okay, so suppose you have 2 functions, right? v1 and v2. Okay, there's two just functions, however they look like. Okay, any function, and you define or you denote by d the distance between those 2 functions. Okay, whatever this distance might be. Okay, so think of 2 functions. Think of x to the power of 2 and x to the power of 8 or something. Then you have 2 functions, and the d is a metric that measures you the distance. Okay, whatever that might be. Okay, that could be a Euclidean distance or any distance metric that you might want to use. Okay, and now we have an operator t, so we do something with those functions. Okay, and then we look how the distance between those 2 functions evolves. Okay, so we look at the distance between the 2 original functions, v1 and v2. Okay, and we apply the operator. That could be anything. This operator, you do something basically with these 2 functions. I don't know. You pick what could be a sensible operator. You choose the maximum, could be an operator, or you add 10, that could be an operator, or you multiply everything by 1 billion, could be an operator, could be anything. And you apply the same operator to the 2 functions, and you measure the distance as well. Then an operator, so the operation that you apply to the 2 functions is called a contraction mapping if this distance decreases. Okay, this is the general idea. So if you have this operator applied to those functions, the distance between those two functions decreases. And the idea here is that if you apply this operator over and over and over and over again, then this distance should be 0, which then implies that the two functions that you initially started with, which are some functions, that those two then are the same, right? So you have a fixed point, and which then helps you at the end of the day in this algorithmic approach to find the form of the, okay. So this is the general idea. Okay, so you have an operator, and this operator is a contraction mapping if the distance between the functions decreases as you apply the operator on those functions. Okay, and this contraction mapping is very nice because it has a fixed point. So those two functions, or applying the operator over and over again, makes those two functions collide, so to say. Okay, and for any starting point, applying this operator over and over again will eventually converge to this fixed point. So it does not only exist, but you also converge to this point. Okay. So the general idea, what you then do is you just assume that you apply this operator t over and over again on the original function v. Okay, so the t superscript n is just the nth application of the operator on that function, and obviously this is the same as the n-1th application of this operator on this function, and from this you apply this operator again. So this is the same. And now what we can do is we can start from 0, okay, and we just construct the sequence, okay, by using this operator over and over again. So we assume that the next function that we have is just the contraction of the original function. Okay, so what we know, for example, is here in this case, if we look at two original functions, so the v0 and the v1, where the v1 is obviously the operator applied to the v0, but this doesn't matter here. Okay, that we then know that the distance between having the operator applied to the function 1 and having the operator applied to the function 0 is smaller than beta times the distance between the two original functions, but that this will obviously be the same. So those two are the same as the distance between 1 and 2. Okay, and now you can maybe already guess somewhat where we are heading. So the idea is now what you can see. Okay, you have the distance between 0 and 1. And the distance between 1 and 2 is smaller than a fraction of this distance. Okay, but then the distance between 1 and 2 is obviously, or the distance between 3 and 2 is then by the same argument smaller than a fraction of the distance between 2 and 1. But this is smaller than the fraction of the distance between 1 and 0. And what you construct is basically a series of all those distances between two neighboring functions. And what you then can use is you can write you can always express the distance between two functions, between two neighboring functions down the road, so to say, as, or you can compare the distance to the distance of the original function. Okay, and then what you can do is, this only applies for neighboring functions. Okay, just for in this sequence of functions that are just close by. But you now could pick any function, okay, or any part of your sequence, and ask yourself, okay, how would that relate to the original function? And since you only have an expression for neighboring functions, you have to somewhat rewrite this distance as a function of the distance between neighboring functions. And here you use the triangle inequality, saying that this distance is always smaller or equal to any detour with which you could reach this distance. Okay.
I think we are running
Oh, we're running out of time. Yes, I'm sorry.
To stop that right in the middle of the derivation, but I think we better continue.
No, that's good. That's good. That was my fault. I should have kept my eyes more closely on the time. No, I think then we just go on Tuesday, and starting here with the fixed point thing. And I think it just takes 15 minutes or so. So it's the rest is not too difficult. And then there are some applications how to implement that. And I think this is then also the more relevant part of what we are doing here. But I think it's important that you just see where things come from, right? If you look it up in a textbook and you stumble upon a contraction mapping, then it's not necessary that you exactly know what happens there, but you have a clue. Okay, this is this crazy thing that we learned about. It's okay that it's there, and but I can go on by doing my things. So okay, thank you so much. Let's call it a day, and have a great day. Well, it's not that great, but still, and have a good rest of the week. Thank you so much.